Hello my dear students, welcome to NEET World. So in this session we will be discussing equilibrium chapter. Okay, so this session will be definitely helpful for your upcoming NEET and also those who are going to attempt their EAPCET entrance exam. Okay, so let us start our session. So in this session I will be discussing both theory as well as concepts which are very important for upcoming exam. Okay, here, so what exactly equilibrium? So before going to start the chapter here, so we know chemical reactions are of two types. One is reversible, another one is irreversible. So this equilibrium will possible only in reversible reactions. So reactions are two types, reversible and irreversible. So this chemical equilibrium, this equilibrium will be possible only in reversible reaction. Okay, so when we say reversible and irreversible, see if a reaction, so reactant R is converting to product. Okay, so if the complete conversion is taking place only in one direction, then we can say that reaction is irreversible. Okay, in some reactions, so some amount of reactant will convert into product. After formation of some amount of product, again this product will reverse back or revert back to the formation of reactant. Okay, so this is how the reversible reactions are taking place. Okay, so in these reversible reactions only, like some amount of product is formed, again this product products whatever it is formed here, that will recombine to form the reactant. So this is what happens in the reversible reactions. Okay, only in those reversible reactions this equilibrium possibility is there. There is no equilibrium in irreversible reaction. Okay, I hope it is clear. The first basic point is clear. Okay, now this equilibrium is of two types again. So one is dynamic equilibrium and another one is static equilibrium. What I am saying, one is static, another one is dynamic. Okay, so whenever we are saying static equilibrium, so here like whatever the like substances participating in the reaction, so complete system will remains constant. There is no movement. Okay, there is no movement in the like reaction. Okay, here when it comes to dynamic equilibrium, so there is some movement in the reaction. It means rate of forward reaction is equals to rate of backward reaction in dynamic equilibrium. So whenever we are saying dynamic equilibrium, the see reaction takes place forward as well as reaction takes place backward. Okay, the rate of forward and backward will be equal. Okay, so that is what happens in dynamic, whereas in static there is no movement. Okay, so all chemical reactions, like generally we can say chemical reactions having like shows dynamic in nature. So dynamic equilibrium, there exists dynamic equilibrium between the reactants and product. That is not the static. So this is a general statement. Okay, so I hope it is clear, there is no confusion here, right? Okay, so what I told you, at the dynamic equilibrium, rate of forward reaction. Okay, for example, A is a reactant converting into product something, let us say B. Okay, so this B again converting back to A. So let us say this is in the dynamic equilibrium now. So it means rate of forward means formation of B is there now. So rate of forward will be equals to formation of A, that is what rate of backward. So RB equals to RF. RF and RB are equal. So this is what happens in the dynamic equilibrium. Okay, so I hope it is clear up to this point, right? Okay, so the state in which observable properties like microscopic properties are there now, pressure, temperature, volume, concentration, density, color, all these are remains constant. Okay, at equilibrium, when I am say equilibrium, at equilibrium point all these terms will remains constant. This is one of the important point. So at equilibrium, pressure, temperature, volume, concentration, all these things will remains constant. Okay, remember this point or highlight in your book. Okay, the next thing is here, so these are a graphical representation. Okay, before going to the graphical representation, let us understand little more about the equilibrium representation. Let us say I have A is a reactant. Okay, A is a reactant, and the next B is another reactant. So let us say these two reactants are combining to form some product C and product D. Okay, this CD again recombining to form the reversible reaction, to show reversible reaction, that is what, again they are recombining, these two are recombining to form BC Bagh, BA Bagh. I hope it is clear. AB are combining and forming this CD. Okay, after formation of CD, after some time this CD are recombining to form this B and A. So that is how the equilibrium reversible reaction is possible, in that equilibrium may exist, right? Okay. So now during these reactions, let us say there are some coefficients also, like A number of A moles of capital A and small b number of this B reactant is there, and here let us say Q moles of C is there, and here P moles of D is there, let us say. So this is how the reaction I am writing. Okay. Now what I am saying, rate of forward. So if we are wanted to talk in terms of forward reaction, so how much fast it is moving forward, so it is represented by rate of forward. RF represents rate of forward. So this depends upon the concentration of reactants. See, initially at the time T0, when we are starting this reaction, we do not have these products, right? We have only these reactants. So at the time T0, we have only this reactant. That's why for forward reaction, what I should write, it is directly proportional to the concentration of these reactants A and concentration of this reactant also B. Okay. Now whatever the coefficients are there in here. So here small a is there now, so write it as a power, and here we have B now, so write it as a power here. Okay. Similarly, now I am asking for rate of backward reaction. So how can I write this rate of backward reaction will be proportional to, see, backward means reaction should start from here now, so this D and C will be the starting materials for backward reaction. So therefore I can write rate of backward reaction will be proportional to the concentration of C and concentration of D, right? Okay. Now what are the coefficients here we have? So stoichiometric coefficients Q and P, write them as the powers. Okay. So this is how we need to write rate equation. Okay. Now here we have like proportionality now. So these we can remove and we can write in terms of their constants, proportionality constant. So rate of forward reaction is equals to, so I can write, I am removing this proportionality, I am writing it as equals to Kf. It means rate constant for forward reaction multiplied with the concentration of A to the power A and B to the power B. So this is how you need to write KRF. Okay. Similarly for this, RB equals to KB concentration of C to the power Q, concentration of D to the power P. So this is how you need to write the rate of forward and rate of backward reactions. Okay. So now at equilibrium, what I told you, at equilibrium rate of forward reaction is equals to rate of backward reaction. It means these two equations can be same, I mean they are equal now. So can I write them like this? KRF means what? KF concentration of A to the power A, B to the power B. Like this we should write, and the next this is equals to RB. It means KB into concentration of C to the power Q, concentration of D to the power P. Like this we have to write. Okay. Now take the relation like this. See, KF by KB if I write KF by KB. So how can I write KF by KB means, so what is the remaining term? If I send this KB this side, we will be having C to the power Q and D to the power P, right? And what is the denominator here? This is the denominator. It will becomes A to the power A, B to the power B. So this is what we need to write. Okay. So I hope it is clear. So how we are writing this KF by KB relation. So we know what is mean by KF. I told you KF is a rate constant for forward reaction and KB is what? Rate constant for backward reaction. So both are constants only, right? So constant, the ratio of two constants again will be a one more constant. So that constant I am writing it as Kc. So I am writing that constant as Kc. Now this Kc is called equilibrium constant. What is that? Equilibrium constant. So now what is the formula for equilibrium constant? The concentration of product rising to the power of their coefficients by concentration of reactant rising to the power of their coefficients. See, Kc equals to Cd, concentration of products to the power their coefficients by concentration of reactants to the power their coefficients. I hope it is clear, there is no confusion, right? Okay. So now, so this is what you need to remember, okay? So in the short form you can remember them like this. So equilibrium constant equals to concentration of product, okay, raised to the power their coefficients, any stoichiometric coefficients are there, write them here, okay. Now concentration of reactants, so these are the reactants, these are the products, right? Concentration of product raised to the power their coefficients, and concentration of concentration of reactant raised to the power their coefficients. Like this we need to write. I hope it is clear, there is no confusion, right? Okay. So now if I wanted to write Kc for this reaction, so A plus B, so now let us take one normal reaction, let us take, okay. So here I am writing, so let us take NH3, formation of ammonia, let us say, N2 plus 3H2 gives rise to 2NH3. So this is what the reaction we will be seeing in Haber's process, right? Okay, for production of ammonia. So for this, how can we write Kc? So we can write Kc, what is the product here? Product is ammonia. What is its coefficient? Stoichiometric coefficient is 2, right? It is a power, okay. Now in the denominator, what is the reactant we have? N2. What is its coefficient? 1. So 1. Next we have H2, concentration of H2 to the power 3. So this is what the Kc equation for this particular equilibrium reaction. Okay, I hope it is clear, there is no confusion, right? And one more thing I want to mention here. See, so this whatever we are writing now, Kc equals to concentration of product by concentration of reactant rising to the power their coefficient. So this is termed as law of mass action or law of active masses, okay. So it means what the effective mass of this particular substances are participating in the chemical reaction is what? The law of active mass, okay, or the active mass involving in the chemical reaction we should say, okay. Now the law of active mass for solid substance, if there is any solid substance is involved in the reaction, so the concentration with respect to that substance is taken as 1, and similarly if any pure substance is taken, the active mass with respect to that substance is taken as 1, okay. For example, here I am writing CaCO3 upon heating decomposes to form CaO plus CO2, okay. Now if you want to write Kc for this reaction, so this is solid, this is also solid, and this is gas, right? So if someone asks you to write Kc for this reaction, so what we can write? Concentration of CaO, okay, right? Concentration of CaO and concentration of CO2 by concentration of CaCO3 we will be writing, generally we will be writing like this, right? Okay. So what I am saying, the active mass or the concentration, molar concentration of the solids will be equals to 1, will be considered as 1. So for this the active mass is 1, for this is also active mass is 1. Therefore Kc will be written as Kc equals to concentration of CO2 only, okay. I hope it is clear, there is no confusion, okay. So I will be explaining few more things now. See, so in this reaction, see the things given here, the reactants and products are given gaseous, right? See, N2 is a gas, okay, let us represent them as gas, okay. So for actually if it is aqueous medium or liquid forms or aqueous medium generally they will be giving, we can write in the terms of their molar concentration like Kc, okay. Equilibrium concentration in terms of molarities we should write like this, okay. Now if I ask you I want to express equilibrium concentration in terms of their partial pressures, because we know ideal gas equation PV equals to nRT, okay. So P equals to N by V RT. It means we can express equilibrium concentration in terms of N by V means what? Molarity. N by V we can express, or in terms of partial pressure also we can express. So partial pressure generally we will be expressing when the reactants and products in gaseous forms. For example, for this particular reaction I have represented in terms of their molarities also. Now we can also write, because all these are in the gaseous state, now we can also write in terms of their partial pressures. So that time equilibrium constant can be called as Kp. Equilibrium constant in terms of partial pressure will be equals to, see, partial pressure of product. Here we have written just concentration. So here we need to write partial pressures. Just make it as P, partial pressure of ammonia. So what is its coefficient? 2. Right here power 2. And in the denominator, partial pressure of N2, because reactant is N2. And how many, what is the coefficient? 1. So P N2 1 power 1 and multiplied with partial pressure of H2 to the power, what is its coefficient? 3. Right here 3. So this is what the equation you have to write. Okay. So I hope it is clear, there is no confusion. Okay. Now I want you to ask one more thing here. What is the relation between Kp and Kc? What is the relation between Kp Kc? Relation between Kp Kc. So Kp equals to, see here pressure equals to C into RT we have now. So by simplifying this, by using these two, and if we are taking the help of this equation, so we will be finally getting Kp equals to Kc RT power delta Ng. Here derivation I am not showing here because we have very less time, right? So just go with this. I hope you already know since you are preparing for this exam. Okay. Anyways, if you want, you can relate them these two things using this equation. You will be you will be getting this kind of final relation. Okay. So what is this delta Ng here? See Kp partial equilibrium constant in partial pressures, and Kc in terms of molar concentration, R is universal gas constant, T is temperature. And what about delta Ng here? So delta Ng is nothing but number of moles of gaseous products minus number of moles of gaseous reactants. Everything should be in the gaseous state, then only you can consider. So delta Ng for this reaction will be how much? Here 2 is there. So delta Ng for this reaction which we are using here is, see products are how many? 2 are there, right here 2 minus how many reactants are there? So 3 plus 1, so it will be 4. All of them are gases. If they are in solid or liquid state or aqueous form, don't consider for delta Ng calculation. Okay. So we have to consider only those which are in gaseous form, right? Okay. So delta Ng for this equation will be minus 2. I hope it is clear up to this point, right? So now Kp will be equals to Kp for this reaction, Kp equals to Kc. So RT power, what is the delta Ng? So minus 2. We can write like this, or we can also write this in terms of so Kc equals to Kp. See minus 2 means what I can write them? So I can write in this format also now. So Kp equals to Kc by minus 2 means I can write in the denominator as RT square. Like this also we can write. Or in the options they will also give in this form, Kc equals to Kp into RT square. So in this format also they will be giving. So all this, even if they give like this, yes, this is correct. Even if they give like this, yes, this is also correct. Even if they give in this format, this is also correct. Okay. So I hope it is clear, there is no confusion. Okay. So there are many questions on this kind of Kp Kc relation, writing the this equilibrium constant equation, this kind of things are there. You can just look into the PYQ questions, and also I will be showing few more questions here, no worries. Okay. Now before going to that, so what I told you, at equilibrium what I told you, at equilibrium rate of forward equals to rate of backward reaction. Rate of forward reaction equals to rate of backward reaction. This is what the point I have mentioned, right? I told you only rate of forward and backward will be equal, but I haven't told you that concentration of reactants and products will be equal. So what I told you, only rate of forward and backward will be equal, but the concentration may or may not be equal at the equilibrium. It means concentration of reactant and product may or may not be equal. Okay. So because see, I haven't directly taken the only concentration, I have multiplied them with this Kf. Here also I have taken the concentration but multiplied with some constant Kb. It means the overall products will be equal, but not their individual concentration. They may or may not be equal. I hope it is clear. Okay. So why I am highlighting that means, just look here. So you need to identify which whether the graphs are correct or not. So they will be like giving 4 graphs. We need to identify which graph is correct. Okay, so now here in the first question, rate versus time is given. So for equilibrium, so whether this graph is correct or not, check here. So at this point, from this point if you observe properly, so rate of forward and backward, both of them are having a single line. It means rate of forward equals to rate of backward from this point. So equilibrium is established at this point. From here onwards it is equilibrium reaction only. I hope it is clear. So this is correct graph for representation of equilibrium reaction. Now here what I told you, after attaining equilibrium, the properties like temperature, pressure, measurable quantities like pressure, temperature and what the concentration, all these things remains constant. Okay, so now see, after attaining, for example, let us draw a line here. So let us draw a line here. So after this line, see, the concentration of reactants and products is being constant. They are not equal, they have their own individual values here. Okay, the concentration is having their own individual values, but that values are being constant after reaching these points, right? Okay, so before this point there is no equilibrium, we can say, but once after reaching this point, see, after reaching this point, so what this can be considered? So concentration of reactants and products are being constant. So I can say, so from this point the equilibrium is established. From here rate of forward, rate of backward will be remains equal. Okay, I hope it is clear, right? So I hope these two graphs are equal. So I will be asking you few more things. See, so for the same graph they might be giving in this format, concentration here and time here. Okay, and they might be giving like this, concentration here, time here. So will this graph is like obeyed equilibrium condition or not? Will this graph is showing equilibrium or not? Okay, and one more thing I'm going to ask you here is, concentration is over. So let us take again concentration, and here I am taking time this side. Okay, so now like this they will be giving random graphs. See, here the curves are not ending up, I mean the values are not remaining constant. See, this is the only point we can see the concentrations are being constant at that particular time, but other than that point there is no constant concentration is observed in the given graph, in the fourth graph. Therefore this is not obeyed, or this is not the suitable graph for representation of equilibrium. But here let us look here. So after reaching this point the concentration is being constant, from this point, right? So I can say at this point equilibrium is attained. I hope it is clear. Okay, so one more graph they will be giving in this format. So rate, so these graphs are very important, rate and time. So I am writing a graph like this. See, so what are the things I have taken? So here I have taken rate, here I have taken concentration as like first one. This is for rate of forward, this is let us say rate of backward. Okay, now tell me whether this graph is suitable graph, whether this graph is representing equilibrium or not, whether this graph is representing equilibrium or not. So this is my question. Yes, so I can see give the number as 5. Yes, this graph is not representing the equilibrium. Why? Because so whenever we are taking rate on the y-axis, that these two lines should merge, they should become a single line. It means rate of forward should be equals to rate of backward at certain point. Then only from that point onwards, if the lines are merged, so we can say that a reaction is in equilibrium. But here the lines were nowhere merged. It means they are having different rate of forward backward values. So I can say this is not the suitable graph for representation of equilibrium. I hope it is clear writing the graphs, drawing the graphs for different equilibrium conditions. Next, at equilibrium, what I told you, all the macroscopic properties like pressure, concentration, density, color, So color will also be remains constant, okay, because since the concentration of products and reactants remains constant, the composition will be having same composition will also be remains same throughout the equilibrium. So what happens, the whatever the color intensity is having, that will also remains same, that's why color also remains constant. So these are the constant things we can remember, okay. I hope there is no confusion in this. Then next, in the reaction, the rate of reaction is proportional to active mass. The statement is known as, what is the statement? In the reaction, let us say A plus B giving rise to C plus T, I am writing, okay. This is a equilibrium reaction. So what they are saying, reaction is proportional to the active masses of the reactants, active masses their active masses they are saying. So what we can say, the active masses, that is nothing but law of active mass. So this is what we have learned, right? So just give me a minute, I just want to check everything is going well or not. Okay. Yes. So which option is correct? First one, right? The next question, the equilibrium constant for the given reaction is, so this is a given reaction, so how can we write equilibrium constant Kc? So it is concentration of products by concentration of reactants to the rising to the power of their coefficients. So I can write Hi to the power 2 because coefficient is 2, and H2 and I2. So this is what the relation we should give. So which expression is correct? So here we have fourth option is perfect for this particular question. Next, which of the following the Kp and Kc values, value of Kp will be equals to Kc. So Kp Kc equal they are saying, Kp Kc are equal they are saying. So in which of these four options this condition is obeyed? So in the first condition, so how can we say? So we know we have a relation Kp equals to Kc RT power delta Ng, right? If delta Ng value is 0, if delta Ng is 0, if it is 0, then something power 0 will be 1, therefore that makes this equation as Kp equals to Kc, right? Okay. So just what we need to do now, we just need to find delta Ng values for each of this reaction. So let me take this one. So what for this reaction you tell me? So here all of them are gaseous. So I can say number of moles of N delta Ng means what? N products minus N reactants. All of them should be in the gaseous state. All of them should be in the gaseous state. Okay. Okay. So now how many products are there? 2. Minus how many reactants are there? Here one gas, here one gas. So I can say 2 minus 2 0. So here Kp Kc is equal, will be equal in the first case. Okay. So now in the second case we can consider, for second case, see products are 1 plus 1 2 minus both are in gaseous state, here also gaseous state 1. So delta Ng is 1. So delta Ng is 1 means the RT is there. So here this is not Kp Kc are not equal. So in this second case Kp equals to Kc into RT power 1. That is what the relation for second one. So for third one what we can get? So delta Ng will be what? 1 plus 3 4 minus 2. So it is what? Plus 2, right? So delta Ng is 2. It means Kp equals to Kc RT power 2. It is not Kp equals to Kc. So this is also incorrect. So only first one is correct. Even for the last one we will be getting 2 minus 3. So it is minus 1. So if we are getting any other value other than 0, in that cases Kp and Kc are not equal. That's it. So only first option is most suitable answer. Okay. If the equilibrium constant for this reaction is K, the equilibrium constant for this reaction is what they are asking. Yes. First of all, write the equation. This is very important. Previously asked questions these are. Okay. This is the equation they given. Equilibrium constant is mentioned as K. Okay. Now the equilibrium constants for this one, half N2 plus half O2 giving rise to NO. For this let us say Kc K dash. So we need to find this K dash. What is the relation between these two, K and K dash? Okay. So what is the observation here we are seeing? So now if we observe these two equations, so what is the difference here we are observing? So this is, if here the coefficients are 1, here it is 2. Now they what they did, they just divided the complete equation by 2, right? If the equation is, if an equilibrium reaction is divided by some number, so the equilibrium constant for that new equilibrium, for this kind of new equation, that will be becomes whatever your like divided number is there, na, so write that number to the power of 1 by n, like this. So for example, if this equation is multiplied by 2, so what we need to do, so Kc will becomes the old equilibrium constant K will be there, na, so to the power whatever the number you have multiplied here. So if we multiplying with 2, we should write it as 2. If we are multiplying with n, we should write it as n. If we are dividing with n, so multiplication means to the power n directly. If we are dividing with that number, that will becomes 1 by n. So here this equation is divided by 2, so it means it will become 1 by 2. So K dash equals to Kc power 1 by 2. So fourth option is correct. I hope it is clear, there is no confusion. Okay. So whenever a reaction is multiplied by n, number n, let us say, so then its equilibrium constant becomes Kc to the power n. If an equilibrium reaction is divided by n, then its equilibrium constant becomes 1 by n. Okay. If a reaction is inverse, then its equilibrium constant becomes, if a reaction is reversed, it means reactants giving rise to products, na. If I write products giving rise to reactant, then the equilibrium constant we should write as inversed form, like this. Okay. Just reverse, if it is reversing the reaction, we should write inverse. So for this reaction, if Kc is 25, the opposite form, like reactants giving products, now if these products give reactant, like in that format if we write, then its equilibrium constant becomes 1 by 25. I hope it is clear. Okay. Then next, here look into this question. N2 plus 3H2, N2 plus 3H2 gives rise to NH3. These are the 3 steps given. So finally they are asking the equilibrium constant K value for this particular reaction. So what is the relation between all these 3 reactions? Check once. So how can we relate K for this reaction? Equilibrium constant is given as K. So how can we relate this K to K1, K2, K1, K2 and K3? So how do we relate them? Let us look here. The first reaction, see, ammonia is there at the product side, but here it is at the reactant side. So by adding them, let us see, I am reversing this equation. So if we reverse this equation, ammonia becomes reactant, right? So whenever we are reversing the reaction, its equilibrium constant will be inversed. It means K should be written as something by K1. I am writing like this because here 2NH3 is there, here also 2NH3 is there. So just they reversed this, right? K1 in the denominator. Whenever we are reversing, equilibrium constant value becomes inversed. That's why K1 in the denominator. Next, okay. Now look, the product NO2, 2NO is there, here also 2NO is there. Product side. It means this reaction is reversed and they added with this. So 2NO is there, which is in the normal form. Whatever here they have, so they included here. So I can write K2 into. Now look into the third equation. So what is the difference between here and here? See, now here we have H2O. How many H2Os are there? 3 H2Os are there. It means what I should do? I should multiply this equation with 3. Therefore, this equation becomes 3H2O. So whenever we are multiplying with that with a particular number, then its equilibrium constant becomes what? The new equilibrium constant will becomes what? That old equilibrium constant K3 to the power whatever the number you multiplied, that number is K3. Yes. So here I should take K3 cube. Okay. So this is what the final equation. So after doing that, see, we got 3 H2O and 2 NO, and you can remove this extra parts, this 3H2, this 3H2, like that. Oxygen also you can balance. Okay, it means 1, plus 3 by 2, that will becomes 5 by 2. Yes, sum is overall it is perfect, right? Okay. So this kind of relation we have in this option. See, K1, no, not in that option. So look here, K2, K3 cube by K1. Yes. So first option is correct for this particular question. I hope it is clear. If you are still facing some trouble to understand, just go back and watch once more. Then that will gives you clarity. So just watch these two questions. If you are still having confusion, go back and once again watch them. That will give you more clarity. Okay. Now Kp Kc is not equal. I just told you Kp equals to Kc RT power delta Ng. See, this is asked in last year 2024. So you have to try for this particular question and take this hashtag question number 1 and write the answer in the comment box. This is again important. For the reaction N2 plus H2 plus CO2 gives rise to these things. All of them are gaseous. If the initial concentration of H2 and CO2 are x moles, if the initial concentration of H2 and these are equal and x mole per liter of hydrogen is consumed at the equilibrium. So let us write that equation first. CO2 gives rise to CO plus H2O. All of them are gaseous state, right? Okay. So what they are saying? Initial concentration of H2 and CO2 are same. Okay. So they are same. They are saying fine. That is, and let us say at a time t0, if the concentration is 1 and 1. Okay. Let us say 1 and 1 is the concentration for both of these H2 and CO2, because they are saying it as 1. I mean same. Okay. And x mole per liters, like x molar concentration of hydrogen is consumed. So after some time t at equilibrium, equilibrium is attained. So T equilibrium, I am writing. So x moles of it is consumed. It means 1 minus x we should write. Okay. If this is consumed x, so this will also be having same number of moles. So it will be also consumed by x moles, because coefficients are 1 and 1. Okay. Now see, from this part only na CO is forming. So how many? So 1 mole giving 1 mole. So here 1 minus x means that same amount of x is formed here. Okay, because this x amount is consumed from here, that will be formed in this manner, like x amount of CO and x amount of H2O. So this is how you should write. Okay. The next thing is, up to here it is clear, I hope. The next, how can we write K equilibrium Kc? At equilibrium we should write concentration of CO, concentration of H2O by concentration of H2, concentration of CO2, right? Okay. So what is the equilibrium constant of concentration of CO? That is given as x. Okay. And for H2O also x into x. So x into x I can write x square, right? So x square I am writing. Next, in the denominator, concentration of H2 at equilibrium is 1 minus x. Okay. For CO2 also, that is also 1 minus x. 1 minus x into 1 minus x, that can be 1 minus x whole square I am writing. Okay. So which option we have like that? So we have first option like that. So we can go with first option. I hope it is clear, there is no confusion, right? Next, Le-Chatterjee principle, one of the very important thing to be discussed. Okay, understanding the dynamic equilibrium. So we already discussed chemical reactions will be having dynamic equilibrium. They will maintain dynamic equilibrium. Okay. So what is the definition of this Le-Chatterjee principle? Let us look here. Okay. In a dynamic equilibrium, so for example, A plus B is in equilibrium with C plus D. This is a dynamic equilibrium, let us say. Okay. Now, so if this dynamic equilibrium is disturbed by changing in the conditions, changing in the conditions means what? By changing some temperature, pressure, volume or concentration of these reactants or products, or if there is any disturbance on the system, so that what happens, the equilibrium get disturbed, right? This equilibrium get disturbed. The position of the equilibrium shift to counteract the change. It means what? For example, look here. If the disturbance is caused this reactant side, so now this equilibrium will shift in a direction to cancel this disturbance, because equilibrium is the most stable state. So what I am saying, equilibrium is the most stable state. If any disturbance is caused to that equilibrium, then this equilibrium symbol is there, na? So that will shift in a direction to cancel out that external stress which is applied on that equilibrium reaction. For example, if the concentration of reactants are increased, now what happens to the equilibrium? It will get disturbed. So therefore, if the concentration of reactants is increased, now concentration of reactants are more than this, no? Therefore equilibrium get disturbed, therefore equilibrium will shift to this side. Why this side? Because the concentration of reactants are more. If by shifting little more this side, what happens? Again they will rebalance, right? Again they will be balanced. The concentration will become again same. I mean that will become constant again. That readjustment will takes place, right? So this is what happens in the Le-Chatelier principle. If concentrations of products are increased, now what happens? So this side concentration of product is disturbed. So if it is increased this side, so equilibrium will shift this side. Therefore again that will be nullify the whatever the extra amount concentration that you have added here. I hope it is clear. Now one more thing I am asking, if concentration of reactants is reduced, if the concentration of these two substances is decreased, what I am saying? So if the concentration of reactant is decreased, now what happens? So if this is decreased, it means here concentration is more, therefore equilibrium again getting disturbed, right? Because at equilibrium there should be one particular value of concentration, right? The concentration should be remain constant, but whenever we are decreasing this, the value is changing. If the value is changed, what happens? Equilibrium getting disturbed. If that is disturbed, so what happens? So in order to nullify the disturbance, so some of these products will be converted into this reactant, therefore again they will rebalance and the reaction getting equilibrium state. Okay, so if concentration of reactant is decreased, so reaction favors or equilibrium favors backward. If concentration of product is decreased, so equilibrium favors forward. I hope it is clear. Now if the concentration of reactants are increased, so equilibrium will shift forward, therefore again the equilibrium re-established. Okay, and one more thing, if concentration of product is increased, again equilibrium getting disturbed, therefore as we increase the concentration of product and equilibrium shift backward and they will again rebalance their equilibrium, they reattain their equilibrium state. I hope it is clear, no confusion, right? Now what are the factors affecting equilibrium? Yes, so in order to understand the equilibrium definition itself, I explained everything regarding this concentration, right? Increasing the concentration of reactant, shift the equilibrium to produce products, more amount of products and vice versa, right? Next, so it means if a reaction is taking place at equilibrium, so at that point we want to produce more amount of product, so what are the chances we can do? So either we need to increase the concentration of reactant, therefore more amount of product is produced, or we need to decrease the concentration of product, therefore equilibrium shift to increase that product concentration, again to rebalance it. So these are the two steps we can take. Okay, now pressure. For gaseous reactions, increasing in pressure shift towards a side with a fewer number of moles. It means for example this is very important point, try to understand here. Okay, effect of pressure, let us see. See here I am taking N2 plus 3H2, that is what the normal Haber's process I am writing here. N2 plus 3H2 gives rise to 2NH3 I am writing. Okay, all of them are in the gaseous state, let us say. Okay, so now here how many gaseous number of moles? See, effect of pressure seen only in the case of gaseous reactions. Okay, that you should highlight. Okay, so here number of gaseous moles are how many? 2 are there. N products which are in gaseous state are 2, and how many of them are N gaseous reactants are there? N reactants which are in gaseous form, how many are there? So these are gaseous, these are also gaseous. 4 gaseous reactants are there. So which side number of moles is more and which side is less? Product side is less now. So for a gaseous reaction, increase in pressure, shift the equilibrium towards the with a fewer number of moles. If we increase the pressure, so the number of moles are more here, therefore equilibrium shift this side. You can remember in this way, this is simplest manner. Okay, so here number of moles are less, therefore equilibrium shift this side when we increase the pressure. Okay, I hope it is clear. Okay, if number of moles are less this side, so that what happens, increase in pressure favors, high pressure favors backward. So here number of moles are less here, therefore high pressure favors forward. I hope it is clear. High pressure favors product formation, low pressure favors reactant formation. You can think in that way. Okay, next, temperature, exothermic reactions. If the reaction is exothermic, amount of like heat is released from the reaction, so in that case system's temperature is getting lowered because heat is releasing out now, therefore temperature will be lowered for the system. So I can say exothermic reactions are favored by low temperature. Okay, so exothermic reaction favors by low temperature. It means for product formation, let us say R gives reactants are in equilibrium with product. Okay, so for this reaction some X amount of heat is released, so X amount of heat is released, so that delta H negative I am writing. If this is the case, so by lowering the temperature, product formation favors. By increase in temperature, reactant formation favors towards reactant, they are saying. Okay, for exothermic reaction, low temperature favors forward, high temperature favors backward. You can remember like this. For endothermic reaction, it means the reaction is favored by high temperature. The reaction is taking place by absorbing heat. Absorbing heat means delta H is positive. Okay, so now in this process what happening, so temperature, initial temperature and after temperature, final temperature is increased, right? So when we compare with the initial and final, the final temperature is rising. It means reaction is favored by absorbing heat. If it is favored by absorbing heat, I can say high temperature favors forward. So for endothermic reaction, if the given reaction is endothermic, okay, it is favored by high temperature. So high temperature favors increase in temperature, shift the reaction product side or forward, we can say. Okay, catalyst. So catalyst will do speed of the reaction without shifting the equilibrium position. So equilibrium will remain like constant, will remain same in the position. So but speed of the reaction increases. Which of the following conditions will favor the maximum formation of product in the given reaction? Okay, this side is a product formation, right? Okay, so this formation is favored by what are the conditions? Okay, so delta H is negative. It means what? This is exothermic reaction. So exothermic, see, negative means heat is released, system temperature is lower. It means in order to move forward, low temperature favors. Exothermic reactions are favored by low temperature. So the option will be low temperature. Both two options are there. Remove this one. Okay, now one more, pressure effect also they are asking, effect of pressure. So just find number, all of them are gases. Here gaseous number of moles are 1 and here these are 2. So high pressures, what they will do? High pressure, when we apply high pressure, the product formation favors more because number of moles are less here. So what is the effect of pressure? So when pressure is applied, then the equilibrium will shift in a direction where there are less number of moles. The less number of moles are product side, then equilibrium will shift forward. Product formation is favored by high pressures. So this is the condition. I hope it is clear, right? Okay. So now what about this low pressure means? So low pressure favors backward. They are asking forward, product formation. So reactant formation means you should say low pressure and high temperature. See, if this side favors by negative temperatures, that side will be favored by positive observing heat. It means endothermic, high temperatures. I hope it is clear, there is no doubt. Why low temperature? Exothermic. Why high pressure? Number of moles are less here. Therefore,